Yeah, sir. Now it is okay. Fine.
Okay, fine.
Micro will do it.
Yeah, microINT. Okay, I'll start again. So this is a microINT interface. MicroINT interface. Here you can see the first option is file. In the file, you'll be having new, open, insert layout, convert layout. So new means what? If you want to design any new design, we'll be using this new option. In order to open the new page or new window of the microINT, we will use this one new. Then open. What is this open? Open is for any kind of earlier designs. If you want to open that window, previously done works, you can open that one. And insert layout. Insert layout is just now like if you have any kind of if you want to design the full ladder. In the full ladders, we know that full ladder can be designed by using two different ways, like by using the logic gates, one XOR gate, then three AND gates and one OR gate, or else we can do it by using by two half adders. So now let me assume that I have already done the work of designing the layout of a half adder, and that particular half adder, if I want to call the layout of that half adder from the previous work, then I can call that particular half adder layout into this present work, and then I can replicate that one. I can copy that one half adder into two half adders, and I can make a connections in order to make it as a layout of full adder. That is how this insert layout will be used. Converting, we can convert into Spice or Spice netlist or CAF layout file. This is layout file. We can convert into Spice programming, Spice netlist we can convert, or layout file you can convert. The next one saying saving of the layout. We can save the layout or save as by, you can give the name of the particular program like full adder or half adder, or else it will be simply, it will take by default example. It will take as an example. You can see here example. We can save it as a half adder or full adder. Then coming to the foundry. Foundry means this is regarding the technology nodes, like 90 nanometer technology, 180 nanometer technology, different technology nodes. Here we can select it. Like selecting the foundry, you have got, you need to enter into microWin. You can see here now. You can see this one 06 rule. Cmos 06 rule is nothing else. It's like regarding 16 nanometer. Like this is like 80. Then again 120. This is 1.2 micrometer technology. 012 means 120. 12 means 1.2 micrometer technology. 018 means 180 nanometer technology. So all these technologies are there. Again 0.25. This is regarding 250 nanometer. So depending upon this technologies, we can use it. 0.35, 50 nanometer technology, FN 70, 90 nanometer technology. So different technologies are there here in this particular foundry option. You can select any one, and we can design the layout by using that particular technology foundry options. Then color. Color is nothing else but here you can make the interface as a white background, or else you can make it as a black background. If I click on switch monochrome, your complete window will appear in this particular format. So white or black, we can use it. So color. Then again, properties, different kinds of properties regarding this one, we can use it. Regarding the layout and lambda values are there here. The minimum layout size and lambda width is given here. For 65 lambda for height, width, and again, this different values are being given. We can see even the technology nodes, electrical nodes are here, NMOS device. We can extract even those values from this property one. In miscellaneous, there are like grids, lambda values are there, and you can name even the file name here. File name can also be named, instead of giving as a default example, you can give it as default some name. That can be done over here. So I'm not entering to the particular detail of the properties. View. In the view, you can see there are some options like refresh, unselect. If you want to unselect any of the part of the layout, you can unselect that one. View all. View all means if you have designed a big structure, then after completing that one, if you want to see the complete layout in one go, in a one particular window, then if you click on view all, the entire window, all that layout structure will be appearing in your one window. Then zooming and zooming out of that particular layout part, wherever you want to check the errors, whether it's connected properly or not. Electrical nodes, lambda grids. These are the small. This one square box will indicate one lambda. Like that, we can take it as one lambda. So that lambda grids are there. MOS slits, different kinds of MOS structures will be available in this MOS lids. And this is regarding this particular. And palette of layers. You can have here different kinds of palettes here now. As I told while explaining the class, that regarding there are different kinds of contacts I told. One is a contact which is used for metal and also polysilicon. So this is the one which is used for metal and polysilicon. See here, you can see it down. Below that one, you can see it is metal and polysilicon. Metal and polysilicon, then again metal and N deficient and metal one. This is N indicates N deficient and metal. This is P indicates N deficient and metal. So these are again few, metal and metal, then again metal 1 and metal 2 and metal. So again, this is regarding, this will generate a complete layout of a transistor. You can directly generate a layout of transistor by this option. So these are few options like capacitors, is there, resistors, inductors. This is like complex contacts. We can use one instead of using only one contact. If you are having a huge width of a layer, you can use different complex contacts. This is regarding VDD supply. This is a high voltage VDD supply, and this one is ground terminal. Clock inputs. These are the inputs. Clock inputs. This is a pulse one. Next one. This is your sinusoidal input, and this is used for obtaining the output visible node. And see here, you can see that different kinds of metals I have told. In this particular software, we are having nearly 6 different kinds of metals. Depending upon if you are having huge number of interconnections are to be done, then you can, in order to differentiate different layers, you can use this different kinds of metals here. Metal 1, metal 2, metal 3, metal 4, and metal 5. Then polysilicon 2 also is there. If you want to differentiate 2 different polysilicons, then you can use polysilicon 2 and also polysilicon 1. This contact, see here, this is a contact which is mainly used for making the electrical contact between VDD and metal, ground and metal, input and metal, and output and metal. So this is a contact used for 4 different ways: for VDD and metal layer, for ground and metal layer, for input and metal layer, for output and metal layer. So again, this is a polysilicon which acts as a great gate terminal. This is a P deficient layer, N deficient layer, and N well. So these are different kinds of layers which we use. Then again, next one is a edit one. In the edit, we can see all this edit options like cut, copy, paste, stretching of the layer, or moving the layer, step by step move. One after the other, we can move it, and you can even see the virtual layouts of resistance, capacitance, and inductance. And there are some like duplicate options, like we can even create some MOS layers for this, whichever you want to specify it. These are the options for that particular work. Then again, simulation. In simulation part, run simulation. We can see there are different kinds of simulation which we can do here in this one, like voltage and voltage. We can do voltage and time. We can do. Then again, voltage versus voltage and current versus time. Then static voltage versus the output voltage, frequency, and time. These are the different kinds of outputs which we can obtain while once if you simulate your layout. And these are the few options regarding that one, and we'll discuss more in detail when we come across the crosstalk. What is meant by crosstalks? UV exposure. We can even try to do the UV exposure MOS layers, and MOS characteristics also we can obtain that one. We'll study about this one in detail later. Then this is regarding the 2D and 3D structure of the cross section of your any of the layout. We can obtain the 2D and also 3D one. Then again, compiling. See, yesterday I spoke about compiling. Compiling of you can compile either one line of the Verilog code, or else you can compile the entire Verilog file. From this option, we can call the Verilog file which you worked in a DSCH, and we can generate the layout of that particular structure which we have worked in the DSCH. This is option used for compiling of the Verilog. Then analysis, different kinds of analysis are there, like parasitic analysis. Design rules check is very important. What is meant by design rule check is that DRC, we call in short as DRC. This is used to check whether all the lambda rules have been used in a proper manner or not. If you don't use lambda rules in a proper manner, then definitely errors will occur and your output will not be generated as we required the output of that particular structure. So these are the few options regarding that analysis. So once if you come to the help option, since it's a student version, you don't have any register option here. So if you enter into the newer version of 3.8, in the 3.8, it will ask for the register. You enter into the register, then it will show your laptops or your PC's node. that particular node has to be copied and it has to be sent to one email which is given in that pop-up message. You send it to the email regarding all the required data, your name and your system node, all those things. They will, within 1 or 2 days, the company will send you the license for your one system itself. You cannot use that license in any other systems. So that can be done by sending a message to the company. Okay, now let us start this particular session by generating automatic layout of a Cmos inverter, which you have already designed in the DSCH, and also we have generated the Verilog program for that one. So I'll start this session with compiling of the Verilog program of the previous work which you have done in the DSCH. So let us start one. So go to compile first, compile Verilog file. Then in the DSCH, you can see here now Cmos inverter. This Cmos inverter, you can click on that Cmos inverter, open. Once if you open this, Verilog file window will appear. See at the what are the Verilog file, Verilog program we have generated in DSCH, which it will appear here. See this one, like module Cmos inverter input 1, output 1, input, output, and it's all the program, switch level program will be appeared here. Then now here, you can click on first compile option, click on compile, then click it on back to editor. When you click this one, your layout will be appeared here. So this is the layout of your Cmos inverter. This is how the microwind will be generating the layout of Cmos inverter, which you have already designed in the DSCH. So for this one, directly you can see the input 1, input 2, VSS ground they have taken here. Then again VDD and output MOS outputs and PMOS and NMOS outputs you can see here. So these are the different type of contacts which you can find here. See, this is a difference between this contact and this one. This is a contact between polysilicon and metal. So whatever the layer you can find here, this is a metal 2 layer and this one is a metal 1 layer. So the software will be using all the layers which is used in the palette. So it will try to use all the different kinds of metals here. So different metals are being used. See, this is one kind of metal layer, this is of one kind of metal layer, and this is of another kind of metal layer. So almost all the different type of metal layers it will use, and it will try to generate the layout automatically for the Verilog program which you generated in the DSCH software by designing the Cmos inverter. So let us now try to simulate this one. Go on, click on this option, run simulation option. If you click on this button, you can see that outputs. See now, whenever the input is 0, the output is going to be 1. Whenever the input equal to 0, output is going to be 1. If input equal to 1, the output is going to be 0. I hope it's clear to you, or else just a minute. I'll try to make it as a monochrome and I'll show it. It looks clearly there. Color, white, monochrome. And now here, this is how the layout looks once if it is in monochrome. Resimulate this one, run option. Now you can see it clearly. If input is equal to 0, the output is equal to 1. Whenever the input is equal to 1, the output is going to be 0. So this is how the layout looks. And you can even find the delay between each and every signal. See now, the delay between the input which you supplied and the delay between the output, it is 6 picoseconds. 6 picoseconds. Again, here coming to this particular transition part, it is the delay between this part and this one. It is equal to 4 picoseconds. So you can even find the delay. Delay can be obtained. So this is regarding okay, frequency. We can no need of here. It's okay. It will be with respect to analog. We can find those things. So this is regarding the delay. This is how we are supposed to find out the delay of your particular design. You can even see here. This is the power consumption. The power consumption of that particular circuit is power consumption of the Cmos inverter which you have designed is 2.059 microwatt. It's a 2.059 microwatt. This is regarding, and you can even see current and volt. See now your input is the input which is supplied is 1 milliampere, and the output of that particular design is 1.2 VDD. This is the characteristics between voltage and the current, input voltage and current, and this is a ID max current, maximum current 0.62 milliamperes, and this is a different kinds of characteristics of the currents, and then you can even find for different options like CNO. This is for voltage and voltage. For this is a it's like a DC characteristics like input voltage and output voltage. So this one indicates the input and this is the output. So characteristics of your CMOS inverter, frequency and time characteristics, you can find even the frequency and time characteristics, and I diagram. This I diagram is nothing else but it's a combination of all the characteristics in one go. You'll get the combination of all the characteristics in one go. This is I diagram. So these are the different